Our second speaker for today is Alessandra Gnecchi from Munich, and she will talk about large and small non-extremal black holes, thermodynamic dualities, and the Swampland. Please go ahead, Alessandra.
Thank you very much. I'm sorry for these difficulties, but hopefully the arrangement will work for the video for Pramod. It seemed very interesting talk. Sorry for making everyone jump. Now I'm going to present a work that recently appeared in archive in a nice German-Italian collaboration between Max Planck Institute and LMU in Munich. I want to thank the organizers for giving me the opportunity to advertise it here. The topic of this work will be an investigation on the parameter space of non-extremal black hole. And our question was in fact to investigate whether limits are in the entropy and temperature parameter space are linked to infinite distance in moduli space, and whether in fact we can give Swampland conjectures looking at a parameter space of non-extremal black holes. So the plan of the talk will be, first of all, some motivation why we're looking at black holes, then some more technical definitions of what is important in this analysis, namely the definition of a metric distance, or a distance at all that makes sense for black hole at finite temperature. And then I will work with the main character of this analysis, which is black holes coupled to scalar fields. And I will give an overview of the results we found by looking at the entropy and temperature parameter space and how we identified towers of states becoming light. So why are we looking at black holes? Well, black holes are a lamp in the Swampland. They've been somehow protagonists from the beginning because we can explain our principles like wave gravity conjecture, the absence of global symmetries in quantum gravity, the completeness of the spectrum, all by looking at black hole physics. And since the beginning, it looks like these black holes and their properties can guide us in understanding what theories can be coupled consistently to gravity in the UV. And they are still an interesting playground. There's many papers in the literature that are investigating properties of black holes. One other reason is that black holes are states in string theory, and there are some of the states that we understand best. They are the focus of one of the greatest success of string theory, namely explaining the origin of the microstates of supersymmetric black holes. It was like first great result that goes beyond our understanding of black holes from Hawking and Bekenstein. And they are interesting states in string theory because they are coupled and charged under multiple gauge fields, abelian gauge fields. And these gauge fields we understand the origin of from D-branes in the internal geometry. And we also understand the origin of the scalar fields that are coupled to these black holes as moduli of the string compactification. So they seem an interesting playground, whether to investigate properties that may be connected with the UV properties of gravity. What we're going to do is we are going to focus on the solutions in the low energy effective theory. So we take strings compactifications and we look at the low energy supergravity theory that has black hole solutions in it. And we are going to try to see if we can formulate some Swampland prediction by looking at the black holes in supergravity or in generic theories of low energy theories of gravity. In order to start our analysis, as I said, we want to investigate the parameter space of temperature and entropy, which characterize general black holes. And we expect that if this is a parameter space, there may be a breakdown of the EFT if we go at limits of this parameter space that correspond at the limit of 0 temperature or infinite temperature or 0 entropy and infinite entropy. How can we quantify this moving in parameter space? We need to find a notion of a distance. And if we think about black hole solutions, well, they are, if they're coupled to gauge fields and scalars, there will be also scalar fields and gauge fields that have a certain profile. But black holes are essentially specific geometry in a 4-dimensional theory or 5-dimensional one. So we can think if we move in a parameter space, moving across different solutions. So we move across a space of metrics. And there is a notion of a metric distance already defined in the context of GR. This metric distance is defined when G mu nu depends on certain parameters and gives us a quantitative way of defining distance between black hole solutions. This is not a new distance. It's been used in the past, also in the context of the Swampland program. It's been used in the derivation of the ADS distance conjecture. And let me stress that when at 0 temperature, an analysis of thermodynamic properties of black holes, in that case related to entropy, has been initiated in this paper using explicitly this metric distance. And there's been other development where this metric has been used. So it seems that we have a hint on how to quantify our investigation of parameter space. We want to connect this distance to a distance, however, in moduli space. Because we know that if we move at large distance in moduli space, a large variation of fields, then we run into problems in a UV-complete theory of gravity. That is the Swampland distance conjecture. And more quantitatively, we expect that if we move at large distance in moduli space, then our trajectory is accompanied by a tower of states becoming massless, and they become massless in relation to the large distance in an exponential way. This is what is, let's say, what is we agreed on is a signal of a breakdown of the EFT, and we want to find a way to relate this to an analysis that looks at parameter space of black hole. So how do we relate this distance in field space to a distance of entropy and temperature? Notice also that we want to find possible criteria that are significant from the Swampland point of view. So namely, if we decouple gravity, our conjectures or our statements should become trivial. In particular, this means that the tower of states that become massless should decouple if we decouple gravity. And this happens, for example, by checking that they have a mass that goes to infinity when we decouple gravity. So the states disappear completely from the spectrum, from the theory. It was found, as I mentioned briefly, that in the previous paper we took inspiration from, by studying at 0 temperature solutions, there was a distance, a notion of a distance identified in terms of an entropy. So the distance in a space of metrics was linked to a distance in parameter space, looking at the variation of the entropy. And so somehow there was also a possible notion of entropy distance conjecture that was put forward, where there was a mass of states that becomes light in this way when we move at large entropy variations in parameter space. However, we are not completely satisfied with this notion of distance for various reasons. It is known that this distance is not diffeomorphism invariant. There are ways that we can redefine it, but we may want to, we may have a problem with that, or we may want to look at the refined definition of distance. Moreover, it's still a distance in the space of metrics, and it doesn't seem like it's directly connected to moduli. How to go beyond? Well, our idea was to look in general at, also investigated in the previous paper, is the idea to consider solutions of black holes that are coupled to scalar fields. Because if there is a coupling between the geometry and the scalar field, then we can aim at finding a relation between the distance in the geometry and the distance in moduli space. However, as we said in the previous case, where an entropy distance conjecture was proposed, there was no real identification of what these states can be at zero temperature. And we want to, in order to generalize these analyses and try to capture more complete description of the parameter space and the limits, we moved to finite temperature solutions. And the idea is that a system at finite temperature may have notion of infinite distance related to them, and also a notion of states that become massless. And to explain better what I mean, let me consider start or move to systems at finite temperature in analogy with compactifications on spatial directions. We know that from compactifications of certain spatial circle, we have a tower of states that is the Kaluza-Klein tower that has scales like n over r. So the scale of the masses of the Kaluza-Klein states is r, which is again it's a dimensionful quantity. So it scales like L Planck. And this is somehow analogous to what happens if we consider finite temperature systems. Because at finite temperature, the system is described in Euclidean time with a compact Euclidean direction of length beta. To these compact Euclidean time directions, there's a natural tower of states that appear, that are the Matsubara frequencies, which are just frequencies that appear in for condensed matter system at finite temperature, and they have a scale, mass scale, that goes like 1 over beta, so proportional to the temperature. So these tower states could suggest a distance in temperature parameter space that is associated to the temperature, and it would signal that when we go at the zero temperature, there's a tower of Matsubara modes that becomes light as temperature goes to 0, or that there is a dual tower of winding modes, somehow some thermal winding modes that become light. Sorry, as t goes to infinity. This was a typo. But this analogy tells us at least that the temperature could become an interesting parameter for the study of distances in parameter space. And so what gravitational systems can we study at finite temperature? Our natural candidates are black holes. And why do we need to go to black holes? At first sight, we could think that, well, there is a notion of temperature even just in flat space. We just change coordinates and go to Rindler's parametrization of flat space. Well, then there is an coordinate horizon, and there is an associated temperature to this space-time that is proportional to the acceleration parameter that enters the change of coordinates from Minkowski to Rindler. However, if you look at the modes, these modes have dependence on the temperature, and the scale of these modes is the acceleration parameter. This acceleration parameter has no information on gravity at all, and so this tower of states does not decouple when we decouple gravity, namely gravity is already decoupled. And so these are not a good tower of states, and in fact, not all of the thermal systems can give us a good, let's say, playground to study, to investigate Swampland criteria. If we want to move to gravitational states, then we need to, at all effects, consider black holes, which are gravitational states, and thermal. The simplest case we can look at is the Schwarzschild black hole. In this case, we can compute entropy and temperature from Bekenstein-Hawking formula, and we can see that in this case we have a tower of Matsubara frequency of Hawking modes that scale like the temperature, and or inversely the square root of the entropy, and these modes decouple when L Planck goes to 0. So this is effect is behaving like a tower of states that we expect become, if this tower of states become light in a certain limit, it may signal an infinite distance limit, because it's a gravitational tower, and it would decouple when we decouple gravity. We can define a distance for Schwarzschild black hole in parameter space, and this distance is given in terms of the temperature or in terms of the entropy, because for Schwarzschild there's only one scale in the game, which is the mass of the black hole. So this somehow is a bit restrictive, because we don't really probe the whole parameter space, but we're linked at this curve of where T and S are constrained to each other. So let's move to something a bit more general. Let's introduce an additional parameter. This additional parameter is a charge. So we're looking now at Dryson-Nordstrom black hole. If we just look at generic mass and charge value, the black hole is a non-extremal, which means it has finite temperature. And we define the non-extremality parameter as m squared minus q squared over square root. And in terms of the thermodynamic variable, this non-extremality parameter is the product of S and T. The associated Hawking modes now are defined just in terms of the temperature, and they are independent, and the entropy is independent on the temperature. So we do have a genuine two-dimensional parameter space. Again, these modes decouple when L Planck goes to 0. So it seems that we are starting to build a more and more consistent setup, or useful setup. However, if we follow the logic that when the temperature goes to 0, an infinite tower of states should appear, then we should look at the 0 temperature limit of our parameter space as an ill-defined place in our low energy theory. So states at t equals 0 should somehow be regarded as a not valid state in the low energy theory. However, at t equals 0, we exactly have BPF states. So we cannot really trust this picture, because we cannot really we know that BPF states are good states in our low energy theory, and so we would like to find something that is more strong to give us an indication that if we have a tower of states becoming massless, then we are at infinite limit in modulus space, and we are looking at solution that should be out of the physical phase space. As I mentioned at the beginning in the introduction, the solution is to add one more ingredient, which is the coupling to the scalar fields. And this seems natural because, as we said, geometry and scalars are coupled by the black hole solutions, and this hints at having the distance in moduli space and the distance in the thermodynamic phase space to be also related. we have looked at two theories or a set of theories. One is the Einstein-Maxwell dilaton theory, and one is n equal to 2 supergravity coupled to vector fields. These two cases have different advantages. In the case of Einstein-Maxwell dilaton theory, we only have one scalar and one gauge field, but we have a generic coupling if we vary this lambda, a positive parameter, so we can scan different theories. However, if we look at n equal to 2 supergravity, we can play with many different models with different number of scalar fields and different number of gauge fields. I will focus to the supergravity case because it makes an easy connection with the string theory setup it comes from, and but all the results are valid for both for supergravity and for the Einstein-Maxwell dilaton theory. What we will find, let me comment the picture on the right. What we find is that there is in the ST plane, there is a region for allowed black holes, non-extremal black holes. That is the region below this blue curve. This blue curve is the Schwarzschild solution at varying S and T. Below this curve, we find all the non-extremal solutions once we vary charges. And we see that this red curve is the curve with constant non-extremality parameter. So it's the ST equal constant curve for a specific value of C. And you can see that we cannot move in this parameter space, varying C in keeping C constant and lowering the temperature. So this, we just have to be careful when we study our region in parameter space. Okay, so just because I will show some formula, let me introduce briefly what I mean, what the ingredients I need to discuss black holes in supergravity. We are looking at low energy theories that come from compactifications on Calabi-Yau in 4 dimensions. And all we need to describe the 4-dimensional theory are basically the prepotential, where these Cij numbers are related to the intersection numbers of the Calabi-Yau, and the scalar fields in the low energy theory are conveniently described by projective coordinates. The number of scalar fields in the resulting low energy theory is related to the number of vector multiplets that indeed are related to the number H11 numbers of the Calabi-Yau. We fix a compactification. So we fix a vacuum, namely we choose a certain value of the scalar field. These give us a Minkowski solution that comes from string theory compactified on a Calabi-Yau with no internal flux turned on. In the low energy theory, there are U1s, and the black hole can have charges under these U1 fluxes when these are turned on. So the black hole charges are just integrals of these electric and magnetic field strength. The most studied solutions in these theories have been zero temperature solutions. They are characterized by a universal near horizon geometry, or the form AdS2 times S2. And because of supersymmetry and zero temperature, actually extremality, these the values of the scalar field are fixed at the horizon of the black hole through the attractor mechanism. This makes sure that the entropy of zero temperature black hole depends only on electric and magnetic charges. However, notice that this vacuum, this near horizon for the extremal black holes is a vacuum that has its own value of the scalar fields. So the scalar fields at the horizon of the black hole need to have a specific value given in terms of the electric and magnetic charges. This value in general is different from the value of the moduli that we chose for our compactification. And that is the meaning of the attractor equations. We choose whatever compactification we have, and because of the black hole solution, the scalar fields run, and they run in space-time until they reach the black hole horizon, and at the value at the horizon that they reach is independent on whatever choices we had of our Minkowski vacuum. It will always be defined by the charges of the black hole only. We focused on a particular model because we wanted to get quantitative results. So we focused on the SCU model. Sorry. The SCU model is, you can see it as just type 2A on T6. The three scalar fields are the volume of these tori, and the volume of the internal geometry is given by the product of these scalars, and it's the scale that gives us the Kaluza-Klein states mass and the dual winding modes mass. But now that we have this volume coming from the internal geometry in terms of the scalar fields of the 4D theory, then we have a distance in terms of moduli. This distance is defined at whatever value of the scalar fields we have. So if we choose a Minkowski vacuum, there will be a distance, a volume that corresponds to the choice of the moduli at the Minkowski vacuum. But if we have a black hole solution and the scalars are running through the space-time, then this volume will travel a certain distance in moduli space as long as we move in space-time. Let me show you the specific example we work with. This is a non-extremal geometry for a black hole in the SU model. We chose the charges Q0 and P1, P2, P3, so 1 electric charge and 3 magnetic charges. This is a generic form of the metric. C is again the extremality parameter. In this metric, what enters is this warp factor that contains the horizon of the black hole. And this warp factor is, depends on the charges, on the value of our moduli at infinity, where we started at the black hole asymptotic, at the Minkowski asymptotic infinity. And it also depends on the non-extremality parameter. The same for the scalar fields. They depend on the charges, on the moduli, and on the non-extremality parameter. But they will run. They will be rho dependence here, if rho is the radial variable, and they will reach a certain value at the horizon. So we are mapping here the radial flow in space-time of the scalars to a flow in moduli space. This is the expression of the entropy and the temperature in terms, as I said, of the moduli at infinity, the non-extremality parameter, and the various charges. So as I promised, this is what enters the solution. And we're ready for our investigation. We are looking at the parameter space, and we have a quantity, which is the volume of the internal geometry computed at the horizon, that tells us how it tells us if there is a tower of states that can become light or heavy, because this volume is, as I said, the scale of the Kaluza-Klein states and the winding states. At the zero temperature, the same volume is just dependent on the charges, exactly because of the attractor mechanism. And in the language of our paper, these the case where I fix the charge Q0 and I vary the magnetic charges was called the type A black holes. But both cases are dual. So what I'm doing is I'm writing the volume of the internal geometry in terms of entropy, temperature, and one fixed charge, Q0. V infinity will be the volume at infinity, at the Minkowski vacuum, where the scalars are fixed at the Minkowski vacuum. So the moduli are chosen at infinity. I will fix this compactification, so I am in a certain theory, and then I'll study what happens in their flow towards the horizon. what do we find? We find an interesting set of limits. For example, let's
Alessandra?
study what happens. Yes.
You have 5 minutes.
Yes, I can finish in 5.
Thank
Thanks.
you.
I'm showing the results. In the parameter, in this region of parameter space, we see that, for example, by taking, by moving in entropy, in temperature, sorry, we can heat the 0 temperature BPS states. This is the T2 limit. But we can also go at 0 temperature, following whatever parabola that goes below the Schwarzschild one. And then in that case, we see that the volume goes like to 0, with the temperature goes to 0, signaling that there's a tower of Kaluza-Klein states that decouples, and a tower of winding states that become light. Following the same parabola, but for t that goes to infinity, we find that in this case, there's a tower of states that becoming light, and that tower is the Kaluza-Klein state. So there, this infinite temperature limit is the compactification limit, according to our analysis. And so we expect, in fact, that our EFT breaks down in this limit. There's also region 3, which is a region of small black holes that where both temperature and entropy goes to 0, that are black holes that we know receive corrections from the string effects. If we vary the entropy, then we have analogous behavior. We hit the 0 entropy axis, the T axis, if we naively go to 0 temperature. And in this case, there's some KK mass that go to 0 because the volume goes to infinity. And however, we expect that somehow there are stringy effects that kick into play the moment we lower the entropy, because lower entropy means lower size of our black hole. So as soon as we go around like black holes of Planck length, there may be order 1 string effects that kick in. If we go at the infinite entropy, we need to go at together with the infinite entropy at 0 temperature in order to remain in parameter space. And then we see that the volume in this case goes to 0. So we have a tower of winding modes that become light. And in region 3, again, we have small black holes, and one can show, for example, that we follow this direction in this way when both S and T goes to 0. So what does it mean? It means that we do have a relation between limits of this parameter space and a related tower of states that become light. And these states can be either Kaluza-Klein states or dual winding states. So what our analysis has told us is that we have a direct, or we can quantify the relation between let's say, an infinite distance in parameter space, ST parameter space, and an infinite distance in, or the tower of states becoming light. And physically, we can identify this tower of states. And we can trust our infinite distance in the thermodynamic parameter space to tell us something about the breakdown of the EFT. In the T1 limit, we reach states at finite temperature but 0 in entropy. And these are somehow singular geometry that are interesting because we don't really know what finite temperature but 0 entropy states are. And we can find them in supergravity in a certain limit. Last thing I want to say is that if we look at if we trust these analyses, where we see that this volume is giving us information on the breakdown of our EFT, then it's interesting to notice that the gauge coupling of the scalar fields to the gauge fields is given by a quantity that, for example, if you take the 0, 0 direction, is exactly this volume. So this is telling us that our analysis is also linking these towers of states are becoming massless with a global symmetry being restored. And that is another, puts it in relation with other Swampland conjecture that are supposed to be somehow related. We've also found some thermodynamic dualities that it would be worth exploring, where S and T go to 1 over S and 1 over T, but also some duality hints at the duality that exchanges T and the square root of S. Because I'm out of time, I'm gonna conclude. I hope I convey that one can actually analyze the breakdown of the EFT by looking at the thermodynamic parameter space of temperature and entropy, that we have quantified how an infinite entropy and temperature distance is linked to appearance of massless towers of states, both identifiable with either the Kaluza-Klein states or the winding states, and these are hinted not just at a entropy distance conjecture, but also the temperature distance conjecture. And we have also found hints at possible thermodynamic dualities that may be interesting to analyze further. And additional directions to explore are, again, connections with other Swampland conjectures, investigate more how the UV theory cures singularities, for example, in the zero temperature limit, zero entropy limit with finite temperature. And there's more directions one can go to in higher dimensions or for rotating black holes. Thank you very much.
All right. Thank you very much, Alessandra, for the very nice talk. Other questions?
Maybe I should give it on.
If you have a question, just raise your hand or just speak up. Okay, so while people are thinking about questions, the effect you were talking about was in the STU model you studied.
Yes, but yeah, it's not very restrictive, if that's your question.
Yeah, go ahead.
Yes, so because of the structure of these so-called cubic geometries, there is a nice generalization to more general setups for different Calabi-Yaos. As long as, for example, you study solutions with charges Q0 and Pi, where Pi can be any other solution, any other number of magnetic charges. This configuration of one zero electric charge and other magnetic charges somehow translates well through different cubic geometries. So these are sort of like generic results. And also I did not present it because for lack of time, but the same limits are found for generic coupling of these Einstein-Maxwell-Diraton theory. So let's say these cover physically the different solutions we know. So the analysis is quite generic.
Okay, thank you. Are there more questions? Timo, yes.
Hi, Alessandra. Thanks for the fantastic talk. At the beginning, you discussed examples where the distance conjecture seems not to give rise to states that would decouple nicely. So does your new analysis now let us understand why this is so, or give criteria when the expectations are satisfied?
There was one case, which is the case of the Unruh temperature, but that was trivial. The other case of
the Schwarzschild, for example, yes. Which
No, the Schwarzschild has an infinite distance that it should be taken seriously. But for example, is the BPS limit,
Right.
I think, which is a finite distance, and we did identify, in fact, let's say, not this this line. So we do not claim that. So our analysis doesn't show an infinite distance at for BPS states, because the volume for the BPS states is fixed by the attractor mechanism. And so because of that, if you are here, but at finite temperature, you still recover a finite answer for the volume. So the limit gives you a finite volume.
I see.
It doesn't give you an infinite tower of states.
Okay.
But yes, it's more clear, the link now with the modular space because of this coupling of the scalar fields, and we can really look at what happens to the volume, which is something that lives in modular space. Thank you for your question.
Great, thank you very much.
Are there more questions? I don't see any. So let's thank Alessandra again for a very nice talk.